Alright, and welcome to Lecture 20, the first part of our 20th lecture in our Probability and Statistics course. So you'll notice that the date on this lecture is the 21st of April. That is Tuesday of the current week, and it is entirely possible that you're watching this lecture on Thursday, as I'm about to post it on late Wednesday, the 22nd. So this is the date that the lecture was actually scheduled for. If you remember, on Tuesday I actually posted the lecture that was the previous Wednesday's lecture. I'm just about a step behind here with getting these lectures up after pushing off one of last week's lectures in favor of getting some grading caught up before you had a midterm. So I apologize for this. I've probably said this to you already, but it has turned out to be a fair amount of work to try to prepare these lectures in this way. And so I'm juggling lots of stuff here. My plan is to have the lecture work caught up by the end of this week, and for next week we should be back on course for posting lectures before the time that we would regularly meet for that course. So we'll be caught up in terms of numbers of lectures, and going forward we should be able to get them up at the time that we would regularly meet for those days. So again, apologies for this. We're all doing our best here, and I'll try to get this caught up this week. Today we are going to begin talking about confidence intervals. So this is our second topic under the heading of estimation of parameters. Last lecture we talked about point estimators, and that is our first method of estimating population parameters. Today we're going to talk about confidence intervals instead. So giving just a point estimate for a population parameter, that would be a single value best guess for that population parameter, is problematic in several ways. When you give such a single value best guess, it does not carry the information of how close you think this guess might be to the actual true value, how big was the sample that generated this guess, and how sure are you? Can you attach some degree of likelihood or some level of confidence to your guess? None of that information is conveyed by a single best guess. If I just say, what is the average mass of a main sequence neutron star, which I don't even know if that's a thing or not. I'm not a cosmologist. But if I ask, for instance, I guess let's do something that I know about. If I say that if I pose the question, what is the average mass of a Quercus alba oak tree, one of the local oaks here in the Hudson Valley? It's the white oak that the American folk, like myself, make bourbon barrels out of. So what is the average mass of a full-grown Quercus alba? And you come back and you tell me it's going to be big because we're talking about a tree, so maybe you come back and you tell me something like 3,000 kilograms. Again, I don't know if that's a reasonable number or not. But that's a single value best guess that you have generated based on some sampling that you've done for the average mass of these trees. It doesn't carry any of the information that we're indicating here. You're not telling me how close you think your guess is, how sure you are of your guess, and similarly, you're not telling me how big was the sample that you took to generate this guess. So it's problematic in several ways. It's good. We like point estimators because we do sometimes need a single value best guess. If nothing else, it gives us sort of ballpark figures as to what it is that we're looking at and what we're working with. But there are other ways to do point estimation of population parameters, and the one that we're going to discuss today is confidence intervals. And it will address many of the concerns that are raised here. So our focus is going to be on population mean as we discuss confidence intervals. We're going to focus on confidence intervals constructed for population mean. It is possible to construct confidence intervals for other population parameters. So you can create confidence intervals for population variance, confidence intervals for some of the other population parameters like mode or maximum and so forth. But our focus is going to be on population mean, and that is going to be largely because the central limit theorem is going to make our lives much easier as we start thinking about confidence intervals for population mean. So that is something to bear in mind. Everything that we do in terms of confidence intervals for the remainder of this course will be us attempting to estimate population mean, but the techniques of confidence intervals do apply more generally. Further, we are going to now assume that we actually know the population variance going into this kind of a question. So we're going to assume that sigma squared population variance is a known quantity for us. And that is not reasonable. This is what mathematicians call a simplifying assumption, and also engineers and scientists will often call a simplifying assumption. It's not true, but we're going to assume it's true because it makes the problem easier. We're going to work through this easy version of the problem first, and then down the line a little bit, we will relax this simplifying assumption, and we will deal with the more complicated but more realistic problem in the next stage. I had a advising mentor, a research mentor, who once said that mathematical research is a process of continual retreat. You pose a difficult problem, you realize it's too difficult, you then formulate a simpler version of the problem, that one is also likely too difficult. You continue to retreat until you find a problem that is easy enough that you can solve it. And then hopefully the solution to that easy version will help you to solve the next most difficult, and then that solution will help you to solve the next most difficult, and so forth. And maybe you'll even make it all the way back up to your original question. So, in that spirit, we will make the simplifying assumption that variance is known. It is unreasonable because if we're trying to estimate the population mean at this point, we're trying to formulate a confidence interval for population mean, it's very unlikely that we actually know variance when we're trying to get some sense of what the mean might be. Mean and then variance are generally the first two questions you would have about a new population, and if you don't have any sense yet of what the mean is, it's very unlikely and unreasonable to assume that you would know variance perfectly at that point in your study of this new phenomenon, this new population. So, not reasonable, but we'll assume it for now. Recall that the central limit theorem tells us that if n is large, in particular if n is greater than, I believe I said strictly greater than 30. I've said greater than or equal to 30 here. We'll call that a typo. So let's say for n greater than 30, the central limit theorem tells us that sample mean for a sample of this size minus the true population mean divided by the ratio of standard deviation to the square root of sample size, that compound expression is approximately a standard normal. This is actually the version of the central limit theorem that includes a standardization having been performed as well. So that is going to serve us here. The idea is that I can calculate sample mean for a sample, and it is population mean that I'm interested in estimating. So what we're going to do is we're going to start by, so we need some confidence interval to think about. There's different confidence intervals you can consider. Generally, you want a high degree of confidence. People commonly talk about 90% confidence intervals, 95% confidence intervals, and 99% confidence intervals. And we're going to consider each of those in turn. There is no theoretical preference for those numbers. They're just sort of the human readable, like those are our inclination. We like those numbers as humans, 90, 95, and 99. We tend to think in terms of those types of percentages. But you can absolutely come up with a 92% confidence interval or a 97% confidence interval, and I'll have you do some of those in the homework and in some examples and sample problems in the next lecture. But let's start by developing the idea of a 95% confidence interval. That's a very common one. The 95% confidence intervals are maybe almost too common in practice. They're sort of what humans default to when we're doing statistics. But let's think about the development of a 95% confidence interval. The first idea involved in finding a 95% confidence interval is the idea that this expression here by the central limit theorem, when n is large enough, is approximately a standard normal. So if I want to find a 95% confidence interval, and I realize we haven't defined those yet, we're working up to that, but in developing the idea of a 95% confidence interval, we begin with the idea of finding an interval such that there's a 95% chance that this expression lands in that interval. So this thing here, this compound expression, is approximately a standard normal. I know how to find probabilities associated with standard normals. So I can find an interval that there is a 95% chance that this approximately standard normal expression lands in. So I'm going to start there. I'm going to start off by thinking about what's the z0 and the z1 such that there's a 95% chance that this expression lands between z0 and z1. And I'm saying approximately 95 here because this thing is not actually a standard normal, it is approximately a standard normal. So we are going to calculate probabilities as if this was a standard normal, and it's going to result in us only having an approximate probability here. So what is the z0 and the z1? The interval that is going to allow that expression to be a or that is going to, what is the z0 and the z1 such that there is a 95% chance that this expression falls between those two values, is what I mean to say. And we can think about that by drawing the density function for our standard normal. Again, our standard normal is z. The density function for our standard normal is the classic bell curve centered at 0. So I'm looking for a z0 and a z1. I haven't specified here that they should be, one should be the opposite of the other, but that is what I'm intending. So I'm looking for a z0 and a z1 such that they lay the same distance from 0 but on opposite sides, and such that there is a 95% chance that a standard normal lands between those two numbers. So z0 and z1 are going to be fixed numbers. Capital Z here is a random variable. I want to fix z0 and z1 such that there's a 95% chance that my standard normal falls between those two numbers. That is to say, I want to pick z0 and z1 such that this central area here the central area is area 0.95. So the area under the curve, under the density curve for the standard normal between z0 and z1 should be 0.95. That is to say, there's a 95% chance that my random variable lands between z0 and z1. That's what I'm looking for. If this central area is 0.95, then the two tails together must make up 0.05, the remainder of the total probabilistic mass of 1, and so each tail has area 0.05 over 2. If this tail is 0.05 over 2 and this tail is 0.05 over 2, together they make up 5% of the total probability, and combined with a 95% in my central region, I have that the area under the density function is 1. So that is going to allow us to find z0 here in particular. We want z0 such that phi of z0, the probability that the standard normal falls to the left of z0, which is to say the area of the left-hand tail here, is 0.05 over 2. 0.05 over 2, of course, being 0.025. So this is where we're able to actually find z0. So at this point, we can look at our chart. We can see what value would you need to plug into phi so that the output is 0.025. And if you do that, you should see that phi of negative 1.96 is approximately 0.025. So z0 is going to be negative 1.96, and by symmetry, z1 will be 1.96. These are our z0 and z1 values. And this number 1.96, because 95% confidence intervals are so famous, and also when we talk about statistical hypothesis testing, the one topic that remains in this course and the last topic that we'll consider, the analog to a 95% confidence interval when you move from confidence intervals to statistical hypothesis testing is alpha values or significance levels of 0.05. And for both of those topics, so here in confidence intervals, we like talking about 95% confidence intervals. When we move to statistical hypothesis testing, we'll like talking about a 0.05 significance level. Both of those concepts are associated with this number, 1.96. So 1.96 plays a particularly important role when it comes to some very standard statistical approaches to different types of questions, and it's a fairly famous number in the realm of statistics. You may have seen it. I've talked to students who've seen it simplified to 2 in like a high school statistics class, for instance, and they were just lying to you. The actual number is 1.96, not 2. So at this point, we have seen that there is approximately a 95% chance that this expression lands between negative 1.96 and 1.96. And now we're going to do some algebra. We're going to start rearranging things inside this probability so that we can ultimately come up with an interval for mu itself, an interval where there's a 95% chance that our population mean lies in that interval. So the first thing I'm going to do is I'm going to multiply all three terms here by the denominator of the middle term. That's going to bring the sigma over root n up into the numerator on the left and right, and it's going to remove it from the central term. The next step is a little bit deceptive. What I'm actually doing is I'm multiplying everything here by negative 1, and when you multiply an inequality by negative 1, you actually reverse the order of the inequality. So I'm going to multiply this inequality by negative 1. This is going to become negative 1.96, and I'll flip the order of these two expressions. That negative 1.96 actually flies all the way over here and lands on the far left. So the probability that this expression is less than or equal to this expression is the same as the probability that negative 1.96 is less than or equal to the opposite of the central term there. And likewise, when I multiply this term by negative 1, it moves and becomes the upper bound. It moves from being a lower bound to an upper bound in that case. So it's a bit deceptive because it looks like nothing changed on the far right and the far left, but in fact what happened was the far right expression got hit with a negative and it moved from the right to the left, and likewise the lower bound got hit with a negative 1 and it moved from the left to the right here. So a little bit deceptive, not something that's going to come back to bite you in practice, but just making clear what happened. And the central term is the only one that apparently changed, and we went from the sample mean to the opposite of the sample mean, and from the population mean, the opposite of the population mean, to the population mean itself here. Once that's done, now I can just add sample mean to all three terms, and I'm going to end up with this as my lower bound, just mu itself in the central expression, and this expression for the right-hand bound. And now we can say that there is approximately a 95% chance that mu lies between this number and this number. And that is the idea of confidence intervals. We want to come up with a random interval which will contain population mean 95% of the time. We're going to talk more about interpretation. That's actually going to be the sole focus of part 2 of this lecture because it is tricky. It's a bit of a subtle point. It's easy to get the interpretation wrong. And I definitely want us thinking carefully about how to interpret these confidence intervals. But saying just a bit about it here, sample mean is itself a random quantity. I go out and I catch 100 crows and I find out what their mass is, and I will have a sample mean for those 100 crows. If I go out and catch another 100 crows, a different 100, I'm going to find a slightly different sample mean. So every time I take a sample of that size, I get a different sample mean, and that's going to result in a different interval that is defined here. But 95% of such intervals that I could create will actually contain the true population mean. That's the idea. Before I actually go out and make my observations, before I write down what interval I found, there is a 95% chance that the interval that I do eventually find will contain population mean. Again, that's me tangenting off, or that's me sidetracking off a little bit into thinking about the interpretation of confidence intervals. We'll put off that to part 2 of this lecture. So we will have further discussion of the interpretation in part 2 of the current lecture. So what we have found at this point is that this interval, sample mean minus my 1.96 times sigma over root n, up to sample mean plus my 1.96 times sigma over n, is a random interval that has a 95% chance to contain the actual population mean mu. So it's interesting, and it's worth noting that this interval is centered on your sample mean. So we've got sample mean, and then we're moving left some fixed amount, and then we're moving from sample mean right some fixed amount. So point estimation of parameters, when we thought about point estimators, we said that sample mean was our single best guess for population mean. And now thinking about confidence intervals, it makes good intuitive sense that your confidence interval would be centered on that single best guess. So that's nice. We have been talking here about 95% confidence intervals. Those are quite common, as are 90% confidence intervals and 99% confidence intervals. Those are sort of the common ones that are talked about. Again, you can talk about 98% confidence intervals. You can talk about like a 14% confidence interval, but there's not a whole lot of utility in presenting an interval that you only have a 14% level of confidence in, that you're only 0.14%, or that you think there is a 0.14% chance that such a random interval will contain the population mean. Generally, you're only interested in confidence intervals for high levels of confidence. These are the most common, but others are possible. All such intervals, each of these three, and all other confidence intervals are covered by this theorem. This is the main theorem for this part of today's lecture. Confidence intervals where variance is assumed to be known. So if you have a population, if the central limit theorem applies to this population, and for the central limit theorem to apply, you'll recall that we need finite population variance, and we need n to be greater than 30 as a rough estimate. And if further you actually know what the population variance is, then the 100 times 1 minus alpha percent confidence interval for population mean is given by this expression. So we've got sample mean minus this z sub alpha over 2 multiplied by sigma over root n, and then the right-hand endpoint for the interval is sample mean plus z sub alpha over 2 times sigma over root n. That's the confidence interval, and the z sub alpha over 2 expression is found by requiring that phi at negative z sub alpha over 2 be equal to alpha over 2. So whatever your alpha value is, and we're going to talk about that more in just a moment here, but whatever your alpha value is, you take that and divide it by 2, and that's supposed to be the area of your left-hand tail in the development that we did just a moment ago. And so you want to find the input to phi that will have output equal to that alpha over 2, so that the area of the left-hand tail is alpha over 2, the area of the two tails together is going to be alpha, and the area of the central region will then be 1 minus alpha. So generally, after I state a theorem, I would talk about interpretation or intuition. I want to put that off. It is an involved discussion, and so we're going to dedicate all of the second part of today's lecture to interpretation of this theorem. We are instead going to think about these z sub alpha over 2 expressions for the 95, the 90, and the 99% confidence interval. The 95% confidence interval, we already did it, but let's do it in terms of this notation. Let's think about it in a slightly different way. So for a 95% confidence interval, this 100 times 1 minus alpha percent expression can be a bit confusing to folks. So we want that. This is the percent of our confidence interval. If we're interested in 95% confidence interval, then we want this to be equal to 95%. That means I need alpha to be equal to 0.05. If alpha is 0.05, I do 1 minus 0.05 gives me 0.95. Multiply that by 100 to get 95, and I'm looking at 95% there. So if I'm interested in a 95% confidence interval, that means I take alpha to be 0.05. And just as we saw prior to the statement of the theorem, we had phi of negative z sub 0.025. We called it z0 in the development, not negative z0, but just z0. But we want phi of negative z 0.025 to be equal to 0.025. So what value can I plug into phi and have the output be equal to 0.025? And if I look at my chart as I did in the development of this discussion, I see that negative 1.96 is the appropriate value for negative z of 0.025. For a lot of folks, what the negative is doing there is weird. It's just part of the formula, like we've got the negative z sub alpha over 2 and the positive z sub alpha over 2. If I scroll back a bit, z1 would be my z sub alpha over 2. And z0 is just the negative of that. It's just a negative number for sure, so that you're taking phi of that to get a left-hand tail that does not involve the main portion of the curve here. So it's sort of an artifact of the theorem. Really, you're just looking for some number that you can plug in to phi and have the output to phi be 0.025, or alpha over 2 more generally. 0.025 here, where alpha is 0.05, excuse me. So this is what we did for our 95% confidence interval, and this was the value, the number that we found that goes into the theorem, the 1.96. If we're doing a 90% confidence interval, then I want this to be 90, meaning I need this parenthetical expression to be 0.9, meaning alpha should be 0.1. So for a 90% confidence interval, we have alpha equal to 0.1, and that means that I want my negative z sub alpha over 2 to be negative z sub 0.1 over 2, which is 0.05, and I want phi at that value to be 0.05. And so I look at my chart, I figure out what can I plug into phi so that the output will be 0.05, and the answer is negative 1.64. If you look at your chart, negative 1.64, phi at negative 1.64 is approximately 0.05. And so this is that z value for 90% confidence intervals, and for 99% confidence intervals we can perform a similar analysis. For a 99% confidence interval, alpha is 0.01, so that alpha over 2 is 0.005. I want some number such that phi at that number is 0.005. I am saying here that I want the area of my left-hand tail to be 0.005. And if I look at my chart for phi, I figure out what the input should be to get this output. And their phi, the negative z value should be negative 2.58. So this 1.64, 1.96, and oh drat. This is a typo. I will fix it in the notes, but this should be a 2.58. I got it right over here, and then I just went on autopilot and did the most common one, the 1.96. So apologies, there's a typo here. This will be a 2.58, but doing it on the left side over here where I got it right. The 1.64, the 1.96, and the 2.58, those are each characteristic of the 90%, the 95%, and the 99% confidence intervals respectively. Our theorem, our big general theorem, has these three special cases which are common. If you want a 90% confidence interval, this is what it looks like. So it's centered on a sample mean. Sample mean is your single best guess for population mean. A confidence interval for population mean is going to be centered on sample mean, but we're going this distance off to the left and this distance off to the right. That's giving me a numerical interval, and in some sense, I am 90% confident that my population mean should fall in that interval. Rather, I'm 90% confident that this interval, once it's calculated, will contain population mean. That's the way I should say that. For 95% confidence intervals, they have this look, as we already discussed. A 99% confidence interval is again centered on sample mean. We go to the left, 2.58 times sigma over root n, and we go to the right, 2.58 times sigma over root n. This should be the same 2.58 here. So this is a lovely little summary, if you fix my typo, of the three most common types of confidence intervals. And that's the basics. So we've got our big theorem for today. This is the formal statement of the theorem. Formal statements always look like if-then statements. And then we've got these three important special cases that we've already explored. This process of finding out what the z-value should be for a 90, a 95, and a 99% confidence interval, that's the process you'll have to duplicate if I were to ask you to find me like a 94% confidence interval, or some arbitrary percentage confidence interval where you don't actually know the z-value ahead of time like you do for these common ones. But in practice, these are the most useful. Alright, that'll wrap part one. I will correct this one typo before I post the notes, and we will reconvene to talk about how to properly interpret confidence intervals. Thank you, folks.